the routing problem.
You could call it a routing problem, yeah, but we'll see it's so much more. So we just want to find the shortest path from A to B, and the numbers indicate the cost or the length on any particular road segment. So take a few minutes to try to find the shortest path. These two graphs are identical. This one is for kind of doodling around on to start with, and then there's a second copy. And if you want a third one, I even have a few extra sheets of it. I do know what to call that. So that's a way to check your work, but if you didn't have me around, how sure could you be that what you had found was the shortest path?
Continue until you find a smaller number.
You could hire a consultant.
Write the program.
So does anyone have what they feel is a good method? Or one that you think is bad, and we'll talk about that. Yeah.
So I got best bet I could at 13.
Okay.
And what I did was I made little vertical lines between the up and down choices. So the first vertical line would be between a 1 and a 0. And the next vertical line would have 5, 4, 7, 3.
Okay, so that one.
Mm-hmm. And what I did is I said, what's the lowest value in each of those vertical lines, and what's that sum? That sum is 10. And I said, okay, I know that's impossible because I would have to make some magical jump between points. And then I tried to do 11, and so on like that.
Okay, so you said, of all these roads I could take from here to here, what's the lowest cost? And if I add up the lowest cost from those, and the lowest of those, and the lowest of those, and the lowest of those, then that, I clearly can't get from one side to the other with anything less than that. So I really like that. That's establishing a lower bound on the problem, right? And then any path you find, you could also compare to that lower bound and say, oh, well, I'm within 3% of my lower bound. Maybe I just want to stop because 3% is pretty good, right? But we don't think you can necessarily achieve it because maybe the first two cheapest things are up here and then the next two are down here, right? You'd have to jump. Okay, so establishing a lower bound, I like that. Any other thoughts or ideas? So if you hit the lower bound, then you know I found an optimal solution. Other ideas?
Local minimums don't really work for this sort of thing. Like if you can't take each segment individually.
Okay.
So you want to go from left to right, you can't go, well, my first issue is in the lowers, combination for that one decision is this.
Okay.
And next
So,
vote.
okay, here's the cheapest,
And then the next cheapest would be
3,
3 and 5, so that's what you at J, and then 2 and 4, put you at P, but that's not optimal.
Okay, so if I just take the cheapest local solution, I go there, and then 3 is cheaper than 7, so I go here.
Yep.
And then 4 is cheaper than 5, so
Yeah.
I go here. And then it ends up pretty much having no choices.
Right.
Okay. But that routing gives me
4 not optimal.
Okay, so that's called the greedy method or myopic. Myopic means short-sighted, like I'm only looking a little bit ahead. And it's not guaranteed to give the best solution. It often gives a reasonably good solution, but it can go drastically wrong. Like, if this cost was $1 gazillion,
You're done.
yeah, the greedy solution wouldn't see that and wouldn't know how to avoid it. Okay, so there's establishing a lower bound. There's a greedy or myopic method. Any other systematic methods you could have proposed?
Did you work backwards?
You can work backwards, and that's the smart thing. We're going to do that. Let me say another dumb thing at first. What if you tried every possible route?
You mean your what?
Okay, how long would you be here, roughly speaking? Or how many possible routes are there? Well, at each of the vertical lines you talked about, I have a decision. I can go up or I can go down as I go to the right. So I'd have to make an up or down decision here, and then another one, and then another one. And how many decisions do I have to make?
2 to the 7 possibilities, is it?
Yeah, there's like 6 vertical lines, sort of. And so that's 2 to the 6 possibilities, which, I mean, wouldn't be here forever. But this is just a small problem. Okay, so let's write down some of those ideas, some good and some bad. Lower bound. Lowest cost segment. There we go. Each vertical line. And you couldn't necessarily achieve that because it might require jumping, you said. But if you did achieve it, then you could stop. Okay, there was greedy method. Myopic is the other word for it. Not guaranteed to be optimal. There's brute force, which to math CS geek means try everything. It doesn't actually involve physical strength. By the way, a path, technically speaking, a path is a collection of segments. So if I just look at like from F to I wouldn't call that a path. That's just a segment or a leg or an arc or a link. A path is the collection of them, and a path is usually connected, unless you can teleport. So a path is like all the way up here and then all the way down. Okay, and there's roughly 2 to the t possible paths. Where t is the number of kind of vertical lines here or something. Now, it's not quite that because, you know, I've got my boundary conditions here. But if the grid was really big, it gives you the idea that this gets big really quickly. Okay, Jeremy's idea was to work backwards. Did you want to tell us more about that?
So I also used like the vertical line idea.
Okay.
Like if I want to get back like to 2 tiers, like
Mhm.
which path should I take to cost least?
Okay.
That's not a very well thought idea.
Okay. Let's see. Did you get a copy of the paper?
Oh, no.
There's a fair. All right. Well, I like the working backwards idea, so let's go with that. So, starting at A is hard. I don't like hard things. I like easy things. I want to say, what's the least cost route to get to B if I start at B? You agree that's easy? And how much does it cost me to get to B if I start at B? 0. Okay, so I'm going to write a 0 right here. Okay, now let's make it a little harder. What if I'm at O? What should I do? I should go down. And how much does it cost me to get to B using the optimal path from O? 2, which is in this case 2 plus 0, right? So I'm going to write a 2 here, which is this 2 plus that 0. Okay, and how about from P? I'm going to write a 1, which is this 1 plus that 0. Okay, well, now let's make it a little harder. If I'm at L, what should I do? I should go to O. And what's my optimal cost to finish if I'm at L? 7. Is that this 5 plus this 2? Plus the 0, yeah. It's really this 5 plus this 2. Okay, so what should I write at M? 4, because I could either go up for a cost of 2 plus 2, or I could go down for a cost of 8 plus 1. So in fact, I could write a 4 if I go this way, a 9 if I go this way, that's the 8 plus the 1, and then write a 4 here. All right, now we can start at H. And 10. How about at I?
8.
8, because it's either 10 if I go this way, 3 plus 7, or 4 plus 4 if I go this way, which is 8. So 8 is the winner there. And you could work backwards from there, right? So the optimal answer is 13, and it's going this way.
So I have a question.
Yeah.
So once you get to like LFN,
Uh-huh.
and it's like you would choose to go through M, I guess, right? Because it's cheaper than going through L or N. Well, actually, never mind.
No, so let's talk about that. You choose to go to M because it's cheaper than going through L or N. But what if it was extremely costly to get to M? Yeah. So this method mixes all that together in just the right way. Is this a lot of work, my suggested backwards method here?
Not for this.
Not for this. And it's all really simple arithmetic, right? Do I have to keep a lot in memory? No, I just have to basically keep one number per node, and there's kind of 4 times 4 nodes. So this is actually a pretty cheap, quick way to do it. This is called dynamic programming. And it's our topic for today. Yeah.
Why is it easier to go back from B instead of starting at A?
There are times of dynamic programming where we want to start and work forward. In this case, we want to work backward. It's a little less natural, actually, to say to work forward in this case. There are times when it's more natural to work forward, but I'd say most of the dynamic programming stuff I see, backward ends up being easier to work.
And just for this one, it seems like equal amounts of work.
Yeah, it probably would be. You just have to phrase things a little differently.
Yeah.
The numbers I'm writing here are what? Like this 4 right here, that 8.
Cost from node winner to destination.
Okay, it's the cost to go from here to the final destination along the optimal path, right? Not just any old cost, but the optimal cost to go. Any questions about my method there?
At the first part,
Mhm.
we went from point B to the node 2. Why would you do that instead of the node 1?
I'm not saying go this way. These arrows just tell me how I'm doing my addition. I got this 1 by adding up a 1 and a 0. I got this 2 by saying, by adding this 2 and that 0. So let me draw a plus sign here.
I just mean, how do you know to start your path by going towards the 2 instead of the 1?
Oh, I don't.
Oh, you don't?
No, I'm
Oh, okay.
I have to figure out the optimal cost to go for each node.
Okay.
So even if like let's say like 1 looks better than 2, right? Why don't I just explore down here? Well, maybe it's costly to get to this region from A. Yeah.
So how do you know that you're cutting off that natural?
I don't cut off any branches. I still explore all the possibilities, but I don't have to remember, okay, I'm trying up, down, down, up, down, and compare that to up, down, down, up, down. So I don't have to remember each possible route. I just have to remember, if I'm here, what's the best thing to do from here on out?
What I meant to say, how is it different than the brute force method? I mean, you're still doing the same number of calculations, right? When you're exploring all the different.
I'm actually doing way less calculations than brute force. I am doing 16 of these calculations because that's how many nodes I have, right? But in brute force, how many possible paths do you have? We said it's like 2 to the 6th,
Yeah.
which is 64. So that's better than that's worse than 16.
Yeah.
And it's not actually that big, but it's still more like 2 to the 5th, 32. And each of those calculations is a sum of a bunch of things rather than a sum of just 2 things and then compare them. So each of those path calculations is longer. And I have to have a system for saying which paths have I already checked and which haven't I. And that's a lot of memory. Okay. Any other questions on our basic idea here? So we're going to introduce some terminology. We're going to say this direction, maybe I'll do it down here. This direction is kind of like time. And we're going to call it stage. And I can number them 0, and then C and D are at time 1, E, F, and G are at time 2, or stage 2. This is stage 3, 4, 5, and 6.
Some people number the stages backwards if they're intending to go backwards, because then you know when I hit stage 0, I'm done. Some people do one, some people do the other. So that's called stage. The other one is called state. And we're going to label this 0, this. So C, I, and O are at +1. E and L are at +2. H is at +3. -1, -2, and -3. We often call state the x variable, even though it's, in this case, it's vertical. And stage we often call t because it's like kind of like time. Okay, any questions so far? So now let's introduce some notation for what we were writing on the grid here. So we're going to call something a value function. V of x comma t is the cost to get from x comma t, and where x is the state and y and t is the stage, to the end along the optimal path. And that's the numbers I was writing on figure. How did I start? I said, let's be lazy.
Start at the end.
Start at the end. So I could write v of 0, comma 6 is 0. That's my final condition. And then what's v of x comma t? Well, let's redraw the diagram. At any particular node, I had like a, let's say this was a 7, this was a 4, and then this cost was 3, and this cost was an 11. So if I'm in this situation, what's the best thing to do? Go up, right? So I'm saying compare the cost to go, if I go up, which is the 3 plus the 7, to the cost for going down, which is 11 plus 4. And I want to take the minimum in this case. So I'd say the 3 plus, and what's the 7? v of x plus 1, because I've moved up, t plus 1, because I've moved to the right. And down is 11 plus v of x minus 1 comma t plus 1. So it's kind of like recursion, right? For computer science people. The difference is, in recursion, you would usually say, okay, I want this number. My function tells me I need these two numbers. So I go call my function to compute these two numbers. That function, which is my own function, says I need these two numbers. So it goes and calls itself for those two. And it builds up a whole stack of calls. The thing is, how often do you use this number? Twice. Once when you're at this node looking this way, and once when you're at this node looking that way. Computer recursion would evaluate that number twice. We're being sneaky by moving backwards, so we only ever evaluate something once. What if I could move directly to the right? Could also move so I'd have same thing, 3, 7, 11, 7 is here. 11, 4, and let's say this was 13 and 2. Then v of x comma t. I want to write something like this for this situation.
Min, up, down, and right.
Mm-hmm. So up, would up be the same as I wrote here? Yeah, the addition of an option here doesn't change what happens up here. So it would be 3 plus, we have x plus 1 comma t plus 1. Down would be the same. 11 plus, we have x minus 1 t plus 1. And what's right?
13 plus v of x plus, or comma, t plus 1.
We're moving to the right. Yes, the t plus 1. T plus 2.
Okay, well first, does x stay the same? It doesn't go up by 1 or down by 1?
Right.
Okay, so it's x, just x, not plus 1 or minus 1. And then what happens to t?
It's moving up by 2, right?
Yeah, it's going up by 2. I'm skipping this stage. Now, I'm writing 3, 13, and 11 here just because I had numbers on the graph, but I'm writing the rest of them generically. I really should write the 3, the 13, and the 11 generically in some way. I could write like C sub x comma t to x plus 1 comma t plus 1 for that one. And write something similar for the 13 with a t plus 2 and x plus 0. So can you see why I didn't initially write this there and just wrote a nice concrete number? That's a pretty big subscript. Okay. Any questions so far? All right, so the homework has you doing something a lot like this. In fact, I think it's exactly this problem. It's provided in Excel. You don't have to do it in Excel. You could write a Java program. You could write a Perl program. You could write a basic program. You could hire someone to do it for you. No. But let's take a look at the way I've got it laid out. Here we go. Or we could just sit calmly and gaze. It's working on it. Okay, so I've got a copy. Oh, maybe I don't have it there. So this network is the same as what we've just been playing with, only turned 45 degrees, because Excel doesn't play with weird stuff like that, right? And this 1 means the cost to go from A to C is 1. The cost to go from A to D is 0. And I think all the numbers are the same as on the sheet we've just been playing with, but if they're not, just use the numbers that are here. So that's the same problem. Over here, I've shown a nice way to organize it. This is saying, so I don't have the arrows now. The cost from A to C is 1. The cost from A to D is 0. What's going on here? Boundary conditions. I didn't really write that when I was writing my v sub x comma t. When I wrote v of x comma t equals this stuff, it looked like you could always choose to go up or down.
You just don't want to.
Yeah, here I'm just saying you really don't want to go this way. That's easier than changing your formula so it's different on the boundaries than it is on the edges, than it is in the interior. So I could type a formula here. The problem is then if I wanted to duplicate that formula everywhere, I'd have to copy and paste very selectively. So it's better to put formulas here, and then you can, like let's say you get all the formulas just right here, then you can fill down and fill over, and it should all work. And it doesn't mess with the numbers you have here. It's a good idea to separate your data and your numbers, right? Sorry, to separate your data and your formulas. So, what would I want to say? If I'm sitting here, I can say, how much does it cost if I go down? How much does it cost if I go over here? Which would be this number plus whatever number is sitting there, right? So I could say this first cell is my V cell. And I could even shortcut the computation and say this is the cost to go if I go this direction. So I could say this cell is the 0 for that one little segment, plus if I did take this segment, where would I end up? At D. What's the cost to go from D? It's that number. And then here, if I went to the right, the total cost from here to the end would be the cost to go on that little segment plus the cost to get to the end from C, which I'm going to store here. So these are like adding the 3 and the 7. The 3 is in the data table at the top. The 7 is in the data table at the bottom, and it comes from formulas that depend on other stuff. And then what do I do with those two things? Take the minimum of them. Doesn't matter what order I use. And then in theory, I can do this and that, and I get a 13. Okay, so your homework is to do that. Or you could do it in Java or whatever else you want. This homework, let's check the grand schedule. Says Thursday.
This Thursday?
This Thursday. I'll email it out after class. Okay, so does everyone have a handle on the basic idea of DP? So if that's so fun and easy, how can we make it more complicated?
Make more decisions, make more solves.
Okay, well the thing about DP is, does it get harder to me as the analyst if this thing was much wider and much taller? Not if I structure things right. So that doesn't make it more fun. I mean, to a certain extent. If I had to go like 10 to the 20th this way and 10 to the 20th that way, then I'm in trouble.
It's not with break.
Yeah. But let's say my car is not very reliable, and I don't care about total cost, I just don't want to get stranded in the middle of nowhere. This seems to be something that resonates with college students.
Yes. Don't
Okay.
prospect.
So what I would really want to do, let's switch back here. I really don't want to go on this segment right there. Right, that's like there's some highway in Nevada where it's like 50 miles between civilization points or something. I really don't want to go on that. And if there's a 6 here, I slightly less, sorry, there's an 8, that's even worse. So I want to find a path from start to end. I don't care about the total cost, but I care about avoiding really long segments. So if I do break down, I'm near a tow truck somewhere. At one of the cities, yeah.
So what, the spreadsheet that you just had up, so you're gonna have the minimum distance up in the upper right-hand corner.
Mhm.
But how do you know which, I mean, that just gives you the that's what I was getting at before.
Mhm.
How's it, because you still have to have the information of which path you took, and that's still gonna end up being like that 2 to the whatever.
Okay,
calculation.
that's good. Let's talk about that. So here I was just writing numbers, right? Could I also go back and write, how did I get this 8? I got it by taking the minimum of 10 and 8. So I could write down which way to go from here, right?
I'll copy it.
No, this is an important point. I'm glad you brought it up.
Because you're still, I mean, you still have kind of the combinatorics or whatever of which direction did I go? I mean, you get to the end, you only get 16 calculations. You got the minimum number, but you
Right.
don't know where you went from that number.
Once you're at the end, then you just take the minimum of each node going back in the other direction. In each,
And
the number
so
of
that's
each
going to be like
intersection.
6. So then you'd add 6, right? And then I guess that would be whatever 22. So that's still less than 64.
So like here, well, anywhere along the boundary, it's pretty clear which way I have to go, right? But here, I got the 4 by taking the minimum of 4 and 9, so I can leave a little marker for myself saying which way to go. So for each node, I have to also store which way do I go from this node. I don't have to store at this node the entire rest of the path. I just know go on this segment, and when you get there, there will be another little sign saying which way to go. So here I have to store one extra bit of information about which way to go at each node, which is pretty easy when I'm taking the minimum. I just record which one was the minimum, up or down. So I end up with, I'd have a arrow this way, arrow this way, arrow this way. I'd have arrows on all the rest of them. I don't know which one it is here, but I'd have some kind of arrow here. So each node has an arrow. And then when I am starting here, I say, okay, which way should I go? Well, I'll follow the arrow. Okay, now I follow the arrow, follow the arrow, follow the arrow. Yeah, so there's two issues. One, finding the shortest path, finding the lowest cost. What's the cost number? 13. And the other one is, how do I actually go implement that? I go up, down, down, up, up, down. In this case. So I like drawing the little arrows on this graph. I do not like doing them in Excel. How would we do that in Excel?
Color.
You take your pen and you write on the screen. Yeah, it's actually kind of a pain to record. Like I said, this thing is the minimum of those two things. That's not so bad. But then actually I could kind of use this cell to say which way to go. I could say if this is equal to that, then use the word up, otherwise use the word down, otherwise use the word right.
I would do 1 or 0 in the conditional format.
Yeah, you could do something like that. Actually, let's do that real quick. So I was saying this is that cell plus that one. This is that cell plus that one. This is the minimum of those two. And then we'll... Okay, so that's the calculation we did before. Now here I could say if this one equals that one, give me 1, otherwise give me 0, something like that. And then I'm deliberately doing this faster than you can type because it's the homework to go back and recreate it. Okay, conditional formatting. And say if it's equal to 1, then color it that way. And then so it's not the most intuitive thing. You have to remember, okay, a 1 meant go down or a 1 meant go right.
You need a key.
Okay, yeah. So yeah, you can do it, or you could say like, if those two are equal, that means go right. So you could put the word right here, otherwise put down. I don't know. Anyway, you get the idea.
Yeah.
So yeah, recording which way to go is not the nicest thing in Excel, but you can hack it together. Okay, so the question is, do we face a combinatorial problem here? Do we still face that 2 to the n problem, or 2 to the t? No, because I'm not storing complete path information. I'm always just storing a little sign saying go this way or go that way. All right. So one of the homework problems says avoid really long routes, really long segments. So you need to rewrite the value function. So the value function, so for part A on all the homework problems, you're writing something like this. You could do this if software never existed, right? And then for part B, you go implement it. And then for part C, which you could do by hand if you want. And then for part C, you're saying, how did this path compare to the shortest path that we did on the very first problem? I think the third homework question says, okay, now instead of treating these as lengths, just say you have a 7% chance of your car dying on this leg. You have a 1% chance of your car dying on this leg, a 2% chance. So whatever the number it is, treat it as whatever divided by 100 as a probability or that percent. Then find the route that maximizes your probability of making it from A to B. So can I say, well, okay, 99% here, plus 96% here, plus 99% here. No. No, you can't add probabilities like that. It's not a very hard fix, but just don't add probabilities like that.
That's done 2,000% of thinking it.
Yeah.
And you want the probability at the end, or you just want the math?
Well, we want both. All right, any questions on that so far? Okay, so let's talk about the fun one.
I'm not very clear on where to find the homeless stuff.
I haven't mailed it out yet.
Oh, okay.
So,
All right.
if you can find it, you're in trouble because it's sitting in my email and not yours. Okay, so then the fun part is called stochastic dynamic programming. Unfortunately, there's another really cool math topic called called semi-definite programming, which also is abbreviated SDP. That's something we sort of talked about in Math 560 last semester. But here's the thing. We're going to say, what if my decisions don't always get implemented properly? So let's say if my decision is to go, let's say down, I don't always manage to go down. Maybe I'm not paying attention to my GPS and I miss a turn or something, right? So maybe if I decide to take the down direction, then I do actually do that with probability maybe 90%. But with 10% chance, I do the wrong thing. And if I decide to go up, then maybe I actually do manage to go up with probability 80%. No reason it has to be the same. The homework has basically this, but it might accidentally switch the 90-10 with the 80-20. Do whatever it says in the homework. So now, I can't just talk about the cost, because the cost could be different depending on what random stuff happens. So now I want to minimize the expected cost. So let's take a little example here. Let's say I have a 3 going that way, and a 7 here. So I have a 4 going this way, and maybe a 12 there. What do I want to do? I want to go up. What's my expected cost for deciding to go up? Well, it's 10 if my decision succeeds.
Are we using a percentage?
So let's use these percentages. So if I decide to go up, then I might get a charge of 10 or I might get a charge of 16 with probability 80% and 20%. So if it's 10 with probability 80% and 16 with probability 20%, what's the expected value? Okay, so you go, the cost, if you end up going up, times the probability of that actually happening, plus the cost if you accidentally go down, times the probability of that happening. What if you decide to go down? It would be something similar. So this 7, is that the cost from here to the end?
Expected cost?
It's the expected cost, including all the randomness that might happen out here. So we're saying v of x comma t is the expected value of cost to go to the end along the optimal path. In this case, what happens first? Randomness or decision? Decision happens first and then randomness. There are problems where they happen in the opposite order. One that I've done some work on is backgammon. In backgammon, you roll 2 dice. I only happen to have one, but okay. No, got the other. So you roll 2 dice, and you say, okay, I got a 6 and a 2, and I could choose to move one of my backgammon checkers 6 and the other one and another one 2, or this other, I can move this other one 6 and this other one 2, or I could move one of them 6 and then 2. So I do some random stuff, and then I get to decide what to do based on that. And you still write this is the expected cost to go, but the difference is here, I say decide, and then I have a sum product. Notice that's a sum product. In this other case, I have a sum product where each of the terms involves a minimum. Like there is a 1 in 36 chance of rolling double ones, and if that happens, then I take the minimum of all the things I could do with double ones. Or I have a 2 out of 36 chance of rolling a 1 and a 2, and then I take the minimum of all the things I could do if I have a 1 and a 2. So it switches the order of the sum product and the minimum. All right. Any questions on that? All right, so let's talk about some cool applications other than shortest path. So let's say you're a biology researcher and you just sequenced the genome of some weird mutant yeast cell, and you want to see, does this sequence match this other sequence I got from a mouse or something? So you'd say, what's my sequence A? Or let's call it sequence 1. And maybe it goes like T, C, G, T, A, C, T. And sequence 2, I go T, C, C, T, C, T. I want to say, how well do these match? Well, you can see this G turned into a C, and this A got deleted. I want an automated way of finding that out. So, I'm going to draw a diagram that's very familiar to you. I'm going to put a node here, and a node here, and a node here, and there, and there, and there. So basically one at each intersection of row and column. It kind of looks like that, right? And I'm going to say, if I think the T in sequence, if I think the first thing in sequence 1 matches the first thing in sequence 2, I'm going to declare it a match and move on to the next thing in both sequences. So I could move that way. So diagonal means I'm declaring this letter matches that letter.
Down would be deletion and right would be an addition of a.
Yep. So down would say, okay, I'm moving on in sequence 1, but not in sequence 2, which is a deletion, or an insertion, depending on whether you're looking at sequence 2 as the main thing or sequence 1 as the main thing. So I have just that same diagram we were drawing. And I want to find what's, so is it surprising to say this T matches that T? No, not very surprising. 0 penalty. If I come down here and I say this G matches that C, like, ooh, that's kind of unlikely to replace a letter by another letter, I'm going to apply a penalty. If I move down, that's a deletion or an insertion or over, and that's even less likely. So researchers have put a lot of time and effort into determining what's the chance that a G turns into a C by random mutation. What's the chance that a G turns into an A? What's the chance that G turns into a T? What's the chance that G gets deleted? So there's penalty matrices for substitutions and deletions. So they're not just theoretical, they actually require lab work. I'm glad I don't have to do it. Okay, here's the bummer. Let's say I have a sequence of length 7, like I do here. How much work does this require? How many calculations do I have to do? Oh, this is length 7 and this one's length 6. So that's like 42 nodes, right? So I have to evaluate my value function 42 times. If this was the same length both times, it would be like 7 squared. So if I want to compare a DNA sequence of length 100 to another one of length 100, it's going to take me how many nodes? 100 squared, 10,000. So on the one hand, it's faster than trying all possible paths, which grows exponentially. But if I have a 100 length sequence and I want to compare it to every single possible gene in the mouse genome, I try it starting from the very first gene, and then try it one letter over, and then one letter over, and it just takes forever. So this is, yeah.
Are you just talking about trying to find the homology or are you trying to find out where specifically the mutation is at?
So this is trying to say,
Just the sequence homology of what you, so you'll get a score at the end and say, well, it's pretty much close.
well,
You
so
don't know where the deletion is.
I'd say, okay, I've got the entire mouse genome stretched out this way, poor little mouse. And I've got a length of 100 that I sequenced from my fruit fly or whatever. And I'm going to compare starting with letter 0 in the mouse genome and my length 100 sequence and get a score. And then I'm going to move my sequence over by 1 and say, starting from base number 1 in the mouse genome, and do the whole calculation again. I'm going to be doing 10,000 things for every point in the mouse genome, and the mouse genome is probably a billion different letters, right? So that's going to take forever. So there are faster ways of searching roughly in the database. They're called BLAST and FAST and other stuff. This is trying for like a absolute minimum cost alignment between two given sequences, but it's too expensive to use in a database search kind of algorithm. Let's see, what else did I want to say there? So it's O of n squared if n is this shared sequence length, or let's just call it the sequence length. So that's faster than the brute force 2 to the n. But still too slow to use as a search mechanism. So there's other ones called BLAST and FASTA, and working on one of those could be your project. Just implement BLAST in Excel or something. All right, so let's say you don't care about biology. You care about airplanes. And you care about that system where you call and if texting doesn't work, and you say departure, and it knows you want to talk about departures, right? How does it do voice recognition? The answer is not very well. It's actually not bad these days. What you do is, or what the computer does is it segments things into syllables. And it says, okay, I heard these syllables, and I want to compare it to this word that I have in my database. And it has a way of matching the sound file for that first syllable against the sound file for the sound op, and saying, is this a good match or not? And once again, same basic diagram as before. So it has a dictionary of words it knows, like operator, departure, arrival, probably every city name, probably times of day. And when you say something, it goes and compares that to all the words it knows. So it's running this kind of procedure. There's only a few thousand words it knows, right? So it's pretty fast. And figures out which word best matches what it heard. So it's pretty neat that voice recognition and DNA sequence alignment work the same way. And then there's what your cell phone is doing right now. When it talks with whatever cell phone tower, it's just saying ones and zeros, and the tower is saying ones and zeros back. But there's some radio noise, right? So it turns out in any, let's say they come in groups of 8, ones and zeros. It's not like you can transmit any old byte you want. There's a restricted set of them. And then it uses like the last byte or the last bit or last 2 bits for error correcting. So if you transmit these 6 bits, then the next 2 bits have to be this particular thing. So then what it does is it says, here's what I heard on the radio. 0, 1, 1, 0, 1, 1, 1, 1. And here's what's in my dictionary. It's actually more like a code book. Not code like cryptography. It's not a secret. It's more like DNA code. It's a system for translating information. And it says, okay, do these two things match? Or is there a deletion? So pretty cool if the same algorithm works in all three applications. This is basically the Viterbi algorithm. It's not quite the same, but Viterbi is now a very rich man and moderately famous because all of modern society depends on this, right? Any questions on dynamic programming?
In what way does the Viterbi algorithm differ?
So what I described here is called the Needleman-Wunsch algorithm. And it's, it comes from biology. I think it's maybe 40, 50 years old at this point. Back then, sequencing DNA was really hard. The Viterbi algorithm is phrased in different words. It's phrased in terms of hidden Markov's model, which we'll talk about in chapter 4. I can't remember exactly what the differences are, but I'm going more on analogies here than exact methods. You could look them up with me. Okay. Let's talk a little bit about scientific literature. In the homework you're working on, which I need to extend at least one day, by the way, it talks about Web of Science.
The citations.
Hmm?
Who's asking the citations, sir?
Yeah. So in the scientific literature, leave some room up here, by the way. Let's say there's the paper you're reading right now. And it cites things, right? So it goes back in time. And cites some old papers. And then, of course, they cite other things. Maybe those two things cite the same thing. Maybe this one cites that thing too. And is that all there is? What else is there? There's newer papers that cite the paper that I'm reading, and maybe also cite something here, and maybe also cite something back there. Does the paper I'm reading cite this? Not unless the author has a time machine, right? Although sometimes it can happen where there's like a draft, and or someone published at a conference, and this cites the conference paper, but then it got officially published later. So there's that kind of stuff that goes on. So is it easy to go from the paper I'm reading to the papers it cites? Yes. Is it easy to go from the paper I'm reading to papers that cite it? Well, it used to be a pain in the neck. Now we have the internet and programs that make logs of what uses up. You used to have to go to the library and look in a book, and you could look up a paper and see what other papers this year have cited that paper. I actually remember that. Okay, then there's the other problem of similar papers to the one you're reading, which might also cite there, and might cite there. Can these cite each other? Well, they're at the same time, so probably not. Or maybe it would cite a draft. So finding similar papers was also a pain way back in the day, because the paper I'm reading doesn't cite it. But now we have Google's, so we have two things. We have something called Web of Science. Can you see why this would be called web? And as far as I know, that's only accessible from on campus, because our campus pays money to them to use it, and so if you're off campus, they don't know. Oh, this is just some average person. Yeah.
You can log in using your email and use it
Yeah.
off campus.
So
first you have to log in while on campus in order for it to recognize you. I just read it.
Okay. So let's say it's only accessible on campus or via a proxy from off campus. And then there's Google Scholar, which does pretty much the same thing, freely available. You go to scholar.google.com. You usually want to turn off the patent searches on that, unless you're really interested in patents. They kind of get in the way. So Web of Science and Google Scholar track all of this kind of forward and backward references. So to get to Web of Science, you go to, let's see, where did I have it? emish.edu/library. Click on Databases. Click on W for Web. And click on Web of Science. And then I search for the author of our textbook here. And selected author instead of topic. And then search. And it brings up stuff he's been writing recently. Now, let's see. Let's try that one. And then you can see here, this paper cited 3 others going back in time. No papers have cited this one yet. It's pretty recent, 2012 or 2013. But you can go backward and forward that way. And the same thing for Google Scholar. So let's try so if I click on any of these, it'll take me to either a PDF of it, or if we don't have access directly to a PDF, you can click on this and it will see what does EMU have access to because we pay for it. And you can see how many times did it get cited. 933 is pretty good, right? Most papers get cited 0 times. But Google's probably giving me the most cited papers at the top of the list, right? Not exactly, but probably pretty close. And then what's related, and you can save citations and stuff. So it's a pretty handy tool.
What's the Web of Science count?
What's the, for that one?
Web of Science 473.
So 450 cite it, but Google said it was 473, so, you can't expect computers to be exact. So it's just a way of exploring the literature, other than just plain Google searching for keywords. Because it's like once you find an article that's really what you want, then following the references is usually more efficient than just Googling keywords. All right. There's a lot more to say about dynamic programming, and I say it in the email. There's inventory problems, like I have this much on hand today, and I send out an order, and that arrives tomorrow, and then I spend the rest of the week selling that stuff, and then I get down to this much inventory, or maybe it doesn't sell and I have more inventory, deciding on optimal ordering policies. So that has randomness in it, right? Because you don't know how much you're going to sell. You don't want to run out, maybe. So all kinds of fun dynamic programming stuff. There are programs that use 10 to the 20th different states, and this book tells how to approximate them because we don't have room to store all the states. Stuff like getting truckers back to their home every 2 weeks so they don't quit your company and go work for another company that's nicer. All right, next time we'll be talking about time series analysis.